Okay, good morning, everyone. Welcome to the Pico-seminar series, which is part of the Pico Electrodynamics Theory Network here at Purdue. So the aim of this network is to really look into the electrodynamic phenomena happening inside the matter at the atomistic level. And as a part of this network, we have a Pico-seminar series where we are really bringing in experts working in different areas of physics, including topological electrodynamic phases of matter, anomalous atomistic waves, angular momentum of the gauge field inside matter. And we had a lot of excellent speakers in this series, both theorists and experimentalists. And today we have another excellent speaker, Professor Dr. Chen-Ting Liao from JILA. And now Dr. Zubin Jacob will introduce him.
Great. Thank you very much, Satwik. I want to welcome everybody to this speaker series and also especially our speaker for today, Dr. Chen-Ting Liao. We are very happy to have him here. He has made many important contributions to really new types of topological states and also spatiotemporal vortices using ultra-fast lasers and attosecond pulses. So I just want to give you a brief introduction about him. So he is a research scientist currently at JILA, a joint research institute at the University of Colorado Boulder and NIST. He also serves as an assistant director of research and knowledge transfer of ST-OAM, the NSF Science and Technology Center on real-time functional imaging. So he did his PhD in 2017 in optical sciences from the University of Arizona. Before that, he's also had some experience in the semiconductor industry. So it's a very broad range of interest. And then he became a postdoc in JILA working on a wide variety of topics, including ultrafast lasers, X-rays, and the applications to probe materials. And he's been a finalist of 2 PhD thesis awards, one of them being the 2019 American Physical Society Carl Anderson Division of Laser Science Dissertation Award. And recently, he actually also won the very prestigious Air Force Young Investigator Award for the year 2023. So with that, I would like to welcome our speaker, Dr. Chen-Ting Liao, and we look forward to hearing from him about various aspects of the topological states of light.
All right, thanks for the kind introduction, and it's a really great pleasure to be here virtually talking about my work. So today I'm going to talk about the topological state of light and darkness, about static, dynamic, and spatial temporal vortices. All right, so to begin with, what we're going to talk about today is topology. I guess many of you in this seminar series know what is topology, right? So topology refers to a spatial property that preserves under continuous deformations. Say if you have an object that after stretching, twisting, crumbling, as long as they are maintained the same, as long as you don't open a new and close a hole or cutting or passing through it, the topology is the same. So that's why for physics, a spherical, its tetrahedral is a sphere, topologically speaking, and the mark equals to a donut. And actually, this kind of topology is quite important for lots of physics phenomena. As many of you might know, that the Nobel Prize awarded to these 3 gentlemen for their understanding, discovery of the electronic and electrical property of materials. But this is about electrical electronic property. But my research is a little bit different. My research actually focused on the magnetic property and optical property. So the magnetic property, I was talking about ferromagnetism, topological spin textures, and so on. And for the optical property, it's about optical vortices. And this area actually have lots of potential application. There's topologies and in different systems, like a topological photonics, topological quantum computer, or topological spectronics, and so on. So today in my talk, I'm going to mainly talk about the optical part, the spatial temporal optical vortice, this part. But I would like to mention that I also work on this topological spin texture, especially on the new method to how we actually probe them. And as you can see here, this is a nice movie that we took, in fact, a while ago, but it just published like 2 or 3 weeks ago, using a new technique we developed, so-called 3D X-ray imaging method. And we can see this topological spin texture down to 10 nanometer scale. And this is 10 nanometer 3D and vector. I'm not going to talk about too much in this magnetic part, but I'm also open to discuss this with you. So I just briefly show this movie about this, the new technique and how we use that to probe this nanoscale topological spin textures. The sample you are looking at here is a nickel sample. And using this new technique, 3D imaging technique, we can actually map out individual spin or magnetization distribution within the sample down to 10 nanometer scale. And since we can map out all this spin texture, we can actually identify a lot of very interesting features. For example, many of you might know there's something called magnetic skyrmions, or it's a three-dimensional version called magnetic hedgehog. And we actually can use this technique to map out all this spin distribution inside this kind of material. And for example, in this case, we found a lot of magnetic hedgehog. And if it's a topological charge equals to plus or minus 1, we also call that topological magnetic monopoles. So they are not real monopole, but it's an emergent particle or the quasi-particle based on the spin textures. So here just shows a two example picture of this magnetic hedgehog, or 3D skyrmion, if you will, with a positive charge and negative charge. So, all right. So in addition to this magnetic part, I'm also working on this topological features in the optical parts. So it's all about light. So let me go to this main theme about the optical vortices. So as many of you might know that optical vortices has been discovered almost 30 years from now. So in fact, light can carry orbital angular momentum. And there's a spin orbital angular momentum and orbital angular momentum. And if you can see my cursor here, the spin angular momentum related to the electric field. Say if we have a circular polarized light, the electric field will just rotate it in time. And on the other hand, orbital angular momentum refer to the phase or the wavefront of this light. And we can take quantized number or integer number to characterize that. And for its intensity pattern of the light carrying OAM, you'll see the donut-shaped distribution. And that's the reason why people always call that donut beam. And if you care about the quantum mechanics, this ST-OAM and OAM actually comes from different parts of this momentum. So if we write down the total angular momentum, and here the linear momentum part is electric field across the magnetic field part, and you can split that into two parts. One part is related to the spin angular momentum, and the other part is orbital angular momentum. And you can write down its eigenvalue, eigenfunction, and know they are quantized, and people usually call that topological charge. So in fact, this kind of topological charge, or also called winding number, things like that, it can be used to describe either this topological charge, either in the material system, in the electromagnetic wave, or magnetic system as well. And the unique feature is about its intensity pattern of this light source, because there's a hole at the center of this donut beam. And because there's an undefined phase, singularity at the center, and therefore the amplitude is 0. And that's why this field, sometimes people also call that singular optics, because it's singularity. And that's the reason there's a title of this talk, Topological State of Light and Darkness, and pun intended, because they start at the center of the beam due to this singularity at the center. And in fact, after the discovery of the orbital angular momentum of light 30 years ago, there's a lot of different kinds of application. For example, researchers use that to perform super resolution imaging, and also telecommunication and optical tweezer and so on. There's just a lot of potential application. For example, if you look at this roadmap of structured light, right now almost has about 1,000 citations. So you know this is a really emergent field with lots of vibrant research in terms of its fundamental properties, as well as all kinds of potential applications. And some of my work also explore using this OAM of light for new application. For example, because I have some background in semiconductor industry, so I'm interested in using this light source for a potential new metrology method. For example, in this case, I invented a new method called using orbital angular momentum of light to do so-called coherent Fourier scatterometry for the defect inspection. The idea is using ST-OAM, then we can actually enhance our measurement for the defect inspection. And of course, since my background is also related to nonlinear optics, attosecond process, so naturally I want to see this kind of light source, not just in the visible infrared light, but actually convert that into extreme ultraviolet UV light or soft X-ray light. So the way we do that is in fact, it's quite simple. The idea is just to start with a visible or a femtosecond pulses carrying OAM, and that could be linear polarized or circularly polarized. But in this particular example I show you here, we can actually use two circularly polarized visible light and the second harmonic. They also carry orbital angular momentum, and we combine them and shine them on a gas target. And after a nonlinear process called high harmonic generation, we can actually convert this visible light, blue light, into extreme ultraviolet light. And because of nature that we have actually two knobs, the two driving laser with different SAM and OM. So we can actually control the orbital angular momentum and also polarization through this process by playing very interesting algebra that's actually related to the conservation angular momentum of OM and SAM. So we can actually control different low topological charge or high topological charge or the circular polarization of a high harmonic process. And here is just an artistic rendering of this process. Just to reiterate that, we can use this light source, get a high harmonic, and actually get a donut beam in the shorter wavelength from extreme ultraviolet light into the soft X-ray regions. In fact, this kind of orbital angular momentum doesn't have to be static. We can have a dynamic or so-called time-varied orbital angular momentum. In fact, the idea here is quite simple. If we started with two femtosecond lasers with, say, topological charge 1 and 2 with some delay, but still overlap, and then we shine them at a gas target to get a high harmonic generation. In this process, the high harmonic pulses we generate will have time-dependent orbital angular momentum. And from the fundamental physics, we know that if we have orbital angular momentum, it's changing, it's varying as a function of time, we actually get a torque. So that's why we also call this kind of pulse self-torque pulses or beams. Because unlike mechanical pulse, once we generate this kind of laser pulses, the pulse itself will change orbital angular momentum. As shown in this figure here, you see within this 20 femtosecond time scale, the orbital angular momentum actually is changing from, say, 17 up to 35. So this is actually a new property of light. Because this is the first time people realize that, well, orbital angular momentum doesn't have to be static. It could be time dependent as well. And that also featured on the cover of Science here, showing how we use a two laser pulses to get this time dependent, time varied orbital angular momentum of light. So if you still remember on my first slides, I talked about the topology. That is a spatial property of blah, 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 blah. But actually, that's not necessarily the case. In fact, this definition is not complete because this kind of topology, or I would say this kind of singularity, could be in spatial, temporal, or even spatial temporal domains. Not necessarily have to be in space. So what does that mean? Well, using a very simple analogy, if we have a spatial temporal, if we have an orbital angular momentum of light, we can think about that as a donut beam like this because of intense pattern. And say this beam is flying, traveling along this z-axis. What if we can flip this donut? Instead of this flying donut, we have this kind of rolling donut. And this rolling donut will have angular momentum pointing perpendicular to its propagation directions. So in this case, we no longer have a spatial OAM. In fact, we have a spatial temporal OAM. And when people first discover this, it's being called spatial temporal optical vortices, or ST-OAM for short. And to understand what's going on with its angular momentum, we can use this analogy. For the conventional OAM, we actually have this propeller of a plane. So its angular momentum, well, of course, this is a mechanical one, but analogy is the same. Its angular momentum is parallel to the propagation direction of this airplane. On the other hand, if we have this spatial temporal OAM, we, instead of airplane, we actually have a helicopter. Here, either the main rotor or the tail rotor will have the angular momentum perpendicular to its propagation direction. That's why this kind of spatial temporal OAM will carry transverse OAM, unlike the conventional one that always has a longitudinal orbital angular momentum. So in fact, the people first observed that back in 2016 when they generate the laser-produced plasma. And what's really get people excited about this is over the past 2 years or so, people realize that we can actually generate this kind of process in a laboratory setting. Oh, and I should mention that the theory, the original theory of this pose, go back here, it's actually proposed back to 2005 in a conference proceeding. But the author never published that to a journal, and somehow people didn't notice this. And it was picked up again by another theorist in 2012. So this was actually predicted a long time ago, but it only realized recently, including the first experimental observation. And I was saying that it's really exciting because now people can actually generate this kind of light sources, spatial temporal OAM, in a controllable fashion in a laboratory using a simple setup. In fact, this whole field is burgeoning. People now also realize that instead of longitudinal transfer, we can have arbitrarily oriented orbital angular momentum of light. But this is just a theory yet. There's no experimental observation. And people also realize, well, we can write down the energy, momentum, and orbital angular momentum for this kind of light pulse. For example, like the equation shown here, that shows the normalized, here normalized is per photon. It's energy, momentum, and orbital angular momentum of such a pulse. But I would say that there's actually still some debate about what's a correct form. Well, not about its energy, but what's the correct form of its momentum and orbital angular momentum. There's a lot of debate still going on. What's a correct form, or what's a coefficient in front of that? Because sometimes there's a coefficient missing, and people are still arguing about this these days. So now I'm going to talk about my work about the spatial temporal OAM. So the first part of the work, I'm going to talk about its nonlinear conversion, because as I told you earlier, I'm interested in its nonlinear optical property or its conversion. So what happens if we have this spatial temporal OAM of light? Can we actually do the nonlinear conversions? Because the idea is that for the conventional orbital angular momentum of light, we can actually do the up conversion, like I showed you earlier, through the high harmonic generation, and you can get the OAM charges, say double or into much higher order through the nonlinear process. How about this spatial temporal version? Can we do the same? So this is how we do our experiment. Well, so we started with say regular laser pulses, and we send these laser pulses into a spatially designed pulse shaper. And the pulse shaper will have the key element, that's a spiral faceplate, that generate actually just a regular OAM in space. But the trick is we have a cylindrical mirror here in this pulse shaper. So in the end of the day, once this pulse coming out of this pulse shaper, instead of conventional OAM, we actually get a spatial temporal OAM. And to characterize that, we just use a delay pulse, that's with a pulse duration shorter than that, and do the interferometer scan. And from the fringe we measure, we can reconstruct this kind of spatial temporal donut, like the one shown on the top there. So this is an experimental reconstructed process. And from the fringe pattern, if I pose here, you can see that what's interesting is this kind of fork pattern. So for those of you familiar with the OAM, this kind of fork pattern is actually how people generate the OAM or measure the OAM. But remember, this is not spatial OAM. This is spatial temporal OAM. So this is actually an interfringe pattern you might expect in both space and time. And if we measure the pulse using a conventional technique like a frog measurement that measure the pulse duration and the retreat phase, you can actually see that there's actually the hole in the middle of this pulse. And after reconstruction, we'll know its amplitude, its phase, or we can plot them together to get this complex field. And I have to remind you that this is not spatial OAM. So one axis space, say millimeters, the other axis is actually time. Okay, so now we have this fundamental pose of the spatial temporal OAM. What do? Well, we can easily, for example, put a nonlinear crystal there and get the frequency double. And we can do the same measurement again. It seems that we get a second harmonic spatial temporal donut. You can see this reconstruction here. It looks much thinner, but what's interesting is about the phase pattern. Instead of 2 pi, now we actually have a 4 pi phase winding here. So indeed, it seems that we have this conservation of spatial temporal OAM or spatial temporal topological charge. It's conserved. But if we change this second harmonic generation process just a little bit, use a thicker BBO crystal, now it seems the conservation seems not good because it seems our donut is broken up and the phase also get a little bit messed up. So what's going on here? So to better quantify and analyze this, we can do the following. For example, we can do the Fourier transform, but not in space, along this spatial and temporal coordinate, do the Fourier transform. And that's what we do here. We can do the so-called modal analysis here. We look at the OAM mode spectrum. For example, this is a fundamental one. Again, we just do the Fourier transform along this azimuthal direction. But remember, this azimuthal is time and space direction. And then do a Fourier transform for the fundamental pulse. And fundamental pulse, we have a topological charge 1. It's very pure. And we get a second harmonic generated. If it's a thin BBO crystal, this charge is closer to 2. But if we have much thicker BBO crystal, we can see an impurity happening here. Instead of charge 2, we also have lots of remaining charges and also high other orders there. So that's why we say this. In this case, we no longer have a perfect conservation of the OAM transferring from the fundamental to a second harmonic process. We call this spatial temporal astigmatism. And to better understand that, we can do some more analysis. For example, we can look at the so-called normalized expectation value of ST-OAM charges. And to calculate this number, we need to extract a quantity called canonical momentum density. Canonical momentum density is actually related to this E electric field times gradient of electric field. And this gradient electric field, and we take the imaginary part of that, and this is actually related to the gradient of the phase. But here, the phase is not in space, but in both space and time. So we can first use this formula to plot the canonical momentum density here. As shown on these yellow arrows, these are the canonical momentum density of our fundamental pulse and the second harmonic pulse in the thin BBO crystal, and also the same canonical momentum density, but in a thick BBO crystal. And then we can calculate this normalized expectation value of OAM charges. And you can see the same thing here. For the second harmonic in thin BBO crystal, we have the number close to 2. But in a thick BBO case, we only have something like 1.36, which is not 2. So that's why we know the nonlinear conversion is not that good in this case. But remember that here, canonical momentum density, we calculate that in vacuum. What happened? So this is a case that we look at the poles after the nonlinear conversion process. What happened inside the nonlinear conversion process? What's this value inside that nonlinear crystal? Well, to better understand that, we need to use a different quantity, and people call that energy density flux. If you look at this formula, it's quite a little bit similar to the momentum density we talked about, because there's also the gradient of the phase term, spatial temporal phase, but there's an extra term here that considering the group velocity delay, the GVD of the material process. So basically, this term just we take the material's group velocity, delay, or dispersion into account. For the fundamental poles, we have this kind of distribution showing on this blue arrows here. And this is a second harmonic thin BBL crystal. This is in the thick BBL crystal. And you can see indeed, it seems that all these arrows point toward this diagonal directions. So that also explains that why we have this kind of weird distribution in our phase. So again, using this both quantity, we now know that we actually have a dispersion that, or the phase match condition, both group velocity phase match and phase velocity mismatch process that's going on. And considering all of them, we just simply call that spatial temporal astigmatism, or the distortion of the poles. So why is this working border? Well, as you might know, that people actually use a conventional OAM and convert that into other type of both electromagnetic wave, like I did, to EUV through high harmonic, but also into other types of wave. For example, people now can generate electron waves, or I would say electron pulses carrying OAM, or also neutron wave, and also mechanical wave, water wave. They can all carry OAM. Now, since there's a demonstration of the second harmonic of a spatial temporal OAM, you might think it's actually very possible that we can also convert this kind of spatial temporal OAM into other types of wave, not just EM wave, but also electron wave, all kinds of matter wave, and mechanical wave. That will be possible. Okay, so briefly, I'm going to talk about the other project that I did. Well, this topic is more for experimentalists, because this is all about measuring spatial temporal OAM. In the past, or including the first project I talked about, reconstructing and measuring that kind of spatial temporal pulse is actually not easy. You need to use a lot of different laser pulses and lots of reconstruction going on to really measure that. So can we do that in a different way? Well, let's step back and think about how we measure conventional spatial OAM. So people do that in different ways. For example, you can use an interference pattern, or there's also creative way using a triangular aperture. And some of my work also use that using a computational imaging method called tychography to measure the OAM. Especially for the multicolor OAM, we can actually reconstruct that. And this is actually important because in X-ray regime, where people don't have an easy way to do, say, interference, computational imaging method will be very convenient. In particular, I like this idea using the symmetrical lens that measure the OAM. The idea is that if you have a spatial OAM and focus that beam through a symmetrical lens, instead of a nice donut, you actually get two lobes like this one. With a charge +1, -1 here, you can see two lobes along different diagonal or anti-diagonal direction. So the question is, can we actually do similar things here and measure spatial temporal OAM? And it turns out that it actually works very well for spatial temporal OAM measurement. So as shown on this cover here, this cartoon artistic rendering here, the idea is that we just need to have two components. One is a grating, one is a cylindrical mirror. And then we can see these two lobes as well, just like conventional spatial OAM. But one axis in space and the other axis in spectral domain. And that spectral domain is related to time domain. And by looking at the different lobes, we can actually know what's going on here. But if we want to have a full reconstruction, we still need to have a reference pose overlap with the spatial temporal OAM pose to do the full reconstruction. Here are just a few examples. For example, if we have a charge 1, we can see these two lobes. Here the axis is Sx and the spectral omega. And if we overlap with a reference pose, we can get a fringe pattern. Then we can do a full reconstruction of this spatial temporal donut in both space and time. And if we have other charges, say in this case, -1, you'll see this two lobe is oriented in a different direction. And for a charge 2, we get 3 lobes, charge 4, we get 5 lobes, and so on. So this is actually a very easy way to measure the spatial temporal OAM of light. And as I mentioned in the very beginning, my interest in both topological property in both light and matter. So I really want to see what kind of interaction or manipulation that we might have. In the past, people have lots of debate about what kind of light-matter interaction a conventional spatial OAM could have. And I'm happy to tell you, right now, it seems debate is more or less settled. As you can see, there are 2 review papers over the past 2 years talking about how does this OAM interact with materials, especially for the condensed matters, chiral molecules, as well as nanostructure. And so now people believe that OAM can actually have a very significant effect on this kind of system, molecule, condensed matter, nanostructures. And it seems there's a lot of new opportunity doing that. But however, at this point, we really don't know what happens if we have spatial temporal OAM of light. Can we also manipulate the material? Can we do some of the change in both space and times? That's still unknown. And one of my current experiment is using high harmonic generated EV beam to look at the skyrmion arrays. And in this case, this is what you are looking at is a magnetic scattering patterns. And the reason we have this 6-fold geometry because the sample here is a magnetic skyrmion lattice in a hexagonal array. And if you do a Fourier transform of this hexagonal array, you know there's a 6-fold symmetry. And after seeing this one, we are interested in using the laser to manipulate these skyrmion patterns. So of course, we can just use a regular laser to pump it. And in fact, that's what we did. And we see the skyrmion will disappear. And if we wait for some time, they'll revive again. And there's already a lot of questions we would like to answer, like what's the energy flow from charge to spin to photon? And what happened to its angular momentum absorbed by this lattice via the spin flipping, photon scatterings? And we also want to know what kind of local or non-local effect this may have. And you can imagine that. What if we change our light source in addition to, if we use the orbital angular momentum of light and to pump the sample? What happened in this case? In fact, there's an exciting experimental demonstration shows that if the OAM line, in this case, is in the UV light, interact with the magnetic material, they will see some kind of dichroism. And this is an experiment done at a Fourier laser in Italy, and the researcher called that magnetic helicoidal dichroism. That simply means that if you have OAM +1 and -1, and your material will respond differently. So we are very interested in this kind of manipulation. For example, how we use OAM of light to manipulate this kind of skyrmion. Can we actually do a different types of control and perhaps for the future all optical switching and things like that. But again, this is just a conventional spatial OAM. We still don't know at this point what happens if we use a spatial temporal OAM to manipulate the material, all kinds of material, including magnetic skyrmion or other type of magnetic topological spin textures. So for those of you who are interested in this exciting, new, emerging, and vibrant field, we actually wrote a paper. It's called the roadmap of the spatial temporal light fields. And I was contributing to a chapter talking about how we use ultra-short femtosecond pulses and its nonlinear frequency conversion. including the spatial-temporal OAM and the time-varying, time-dependent orbital angular momentum of lights. So there's a lot of exciting experiment going on from the basic understanding, like energy, momentum, things like that, including how to generate them, how to characterize them, and also how to use them for the potential future applications. So yeah, I encourage you to look at this paper. Right now it's posted on the archive, and the paper is under review for this new roadmap paper about the spatial temporal light fields. All right, so in summary, so in this talk, I mainly talk about the topological property of light field, but my research also covers the topological property of the magnetic, spatially using the light. Well, in this case, it's X-ray light, how we actually probe them, imaging them, and potentially manipulate them, and see if we can have an exciting potential future application like optical switching, or better understand the skyrmion or hedgehog, this 3D version of skyrmion for the future spintronics. Well, people call that skyrmionics these days. So with that, I'd like to thank you for your attention and open for questions.
Great. Thank you so much, Chen-Ting. This was a really excellent talk, and all your figures are really excellent, especially the X-ray 3D movie is really wonderful. So it was a pleasure to hear about all your activities. So we would like to now end